Hi. So today I'm going to be talking about evolution, vision, adversarial networks, and StyleGAN-T. So evolution, I was thinking a lot about what I wanted to do my final presentation on, and one of the things that kept coming back to me was those optical illusions we had at the beginning of the semester. Um, so we have a lot of these sort of flaws in our visual perception system, and why is that? And well, often it's because those kinds of flaws are actually evolutionarily advantageous to us. So if we look at this view on the right, these two sort of blocks placed on top of each other, the bulk of them are the same color, the same sort of brightness. However, we perceive the top one to be darker than the bottom one. Now, this is based evolutionarily on, for the vast majority of the time, us, meaning our ancestors, uh, seeing the world with only one light source, which is from above, the sun or the moon or the stars. And hence, when we see something that is top lit and the same brightness as something which isn't top lit, the thing that is top lit must innately be darker than the bottom thing, and therefore we perceive the top image, the top block, which is sort of angled upwards, to be darker than the bottom one. So this again brings me to one of my favorites. It's the Donald Hoffman fitness beast truth hypothesis, which is about how when there's an evolved creature or system, um, the system which adapts to perceive things in the most evolutionary beneficial way, or adaptable or survival based way, fitness, always beats out the system which will perceive the system, the organism that will perceive the system with the most truth. This is called this fitness beats truth hypothesis. Some interesting things over here. Again, you look at the snake's head on the bottom left. Obviously, the image itself of a snake's head doesn't pose any danger to us, but the snake itself does. So having this sort of fear associated with the snake is advantageous to us. So we don't approach it. And then again, you have these caterpillars on the next one over, which can sort of have evolved to mimic a snake's head appearance, and that's to frighten us off. So there are lots of ways of hijacking these systems. And why am I thinking about these sort of? So while I'm thinking about this sort of snake and caterpillar, I'm thinking about sort of organisms which are sort of co-evolving, and sort of features that as one evolves, the other organism will sort of continuously evolve features which sort of shift back and forth. One of my favorite little versions of this comes from actually Futurama. There's a really little funny sequence about two organisms which are co-evolving. At first, they evolve to sort of one stands on top of the other, so they can reach this sort of food source. And the red one realizes this is sort of an evolved pattern over generations, goes, oh, I'll just start eating the blue organism. Then the blue organism starts to inflate itself to beat the red. And then the red evolves sort of a stinger to pop the blue balloon. And then the blue evolves armor, and so on and so on. And, when you have these sort of organisms existing in the same environment, they accelerate each other, and they push each other in the same direction. So I was thinking, how can this be applied to machine vision? And how can evolution be applied to machine vision? And I was brought back to generative adversarial networks, GANs. So, as we know, generative adversarial networks are designed to generate images, which are generally designed that are supposed to be able to pass as part of a data set. They do this by creating these sort of imitation images from a set of random input integers. And they try to make these imitation images as close as possible to images from the data set. Importantly, this is done with two adversarial loss functions which co-evolve simultaneously. The first is within the generator and is trying to make the generated image similar to the dataset images. And the second loss function is part of the discriminator, which is trying to differentiate the dataset images and the generated images. So when we come back to these sort of handwritten datas, yeah, the data set would be a lot of pixel diagrams of handwritten digits, can be encoded. And the random integers here will be connected to a fully connected layer of a neural network, which will then take each of these sort of integers and transform them into a pixel image. This is often sort of upscaled from a low dimension integer set. And then this generated pixel image is encoded. And these two encoded images are tested against each other in the discriminator, which will sort of detect whether an encoded image is a real part of the data set or not. with each iteration of the training that the model goes through, the loss function applied to the generator's weights is trying to maximize how much the generated image passes through the discriminator, and the discriminator with each generation is trying to maximize making only the true original images, as in from the training data, detected as part of the data set. And this way, these sort of two loss functions sort of are fighting against each other. And as the generator becomes stronger, the discriminator is not only sort of learning, I'm going to use learning here, evolving. The discriminator is not only learning how to discriminate just generally better, but specifically is learning to discriminate higher, sort of sneakier features that the generator creates. So as the generator sort of evolves more advanced feature creation, the discriminator has to sort of step by step beat out those features, which kind of, you know, bring us back to this these sort of two aliens. So now I'm sort of thinking about, okay, adversarial networks create an evolution of vision that is, you know, maybe somewhat more similar to humans. Not really at this level. There's sort of just the idea of two sort of systems which are sort of fighting against each other. I'm thinking about humans and how we sort of evolved in natural environments where, you know, our survival is with other organisms and is reduced by other organisms. But again, at the same time, as other organisms become more sort of adapted to our environment and maybe more aggressive and taking up more resources and sort of becoming more, you know, predatory, we sort of are forced to adapt. So this sort of generator and discriminator idea is quite maybe an interesting analogy to sort of organisms competing for resources, you know, predators, you know, what threaten to consume us, or microorganisms break us down. You know, generations of, you know, more and more advanced networks can maybe even be taken as, you know, when parents have offspring, though they come along to sort of take over. And I'm trying to think about what kind of human vision, how can I bring human vision into this? And I was thinking back to sort of faces. And, you know, we have this sort of Young et al. Paper, which showed that, you know, non-composite faces don't really look like faces and are sort of a lot harder to take a lot longer for us to perceive as faces. And importantly as well, that when you have upside down faces, you don't see them as faces in the same way. So I'm thinking about, okay, why might this be? And thinking about how we actually already see a lot of faces in lots of different inanimate objects in life. You know, this thing called pareidolia. However, with faces in humans, the natural orientation is generally upright, so we only would ever need to identify them upright. It would be energetically unfavorable if we were seeing faces in everyday objects which are upside down, and therefore it might make the most sense then. You know, we have this, we know already how we have this sort of vertical plane of vision, of sort of the sort of bias of things being top lit. So why not that we have sort of faces being sort of oriented upwards so that we aren't distracted by seeing faces in, you know, upside down images. Sort of help express this, you know, babies, we can sort of, they prefer to track a paddle which looks more like a face with the two eyes and mouth than something which sort of doesn't really look like a face at all. You know, even though this is the same sort of set of shapes, because it's oriented upside down, our brain might, you know, not want to waste the energy of identifying that as a face and sort of therefore processing it in the same way we'd always process faces of, oh, is this a relative? Is this a, you know, a rival? Is this, what is this? And then I was thinking a little bit about how, you know, our vision might have co-evolved with other sort of organisms. So I then looked into how we perceive food. Found this quite interesting paper. And it basically talks about how we equate brightness of different colors to different calorie scores, and different sort of perceived edibility. So it tends to be that red foods are perceived as more tasty, as having a higher calorific content, and things with more green in them are tend to be perceived as less calorific and less sort of tasty, less desirable. Why might this be? Yeah, it could be part of this sort of perception of a truth, that, you know, maybe it actually just happens that calories are red and lack of calories is green. But in reality, going back to this sort of idea of fitness beating truth in terms of our perception, you know, if we can perceive things that are calorific as this sort of bright, standout color, that's really useful for us because we can see it more easily. At the same time, when we think about these two sort of organisms which are co-evolving, when we have these sort of fruit-bearing plants that want to be consumed and have their seeds disseminated, they can then sort of hijack that system that you know, our ancestors may have evolved to sort of see things and sort of start producing these pigments. So they can really, really lean into that. And so at the same time, you know, we can have this sort of relationship where two organisms are competing, or we can have this relationship with, you know, humans and plants where obviously this is, you know, sort of more selectively bred, but, you know, having these red fruits that we can see and eat and, you know, pass on the seeds is useful for the plant and useful for us. So I'm thinking about how we sort of co-evolve, like with adversarial networks, and then thinking a bit about more how can we have these sort of, you know, evolution of features in a non sort of biased, pre-biased way. You know, so then I came to contrastive learning, which is a form of self-supervised learning. And I was thinking about how we can have this sort of learning and adaptation without, you know, the initial input, which might sort of, you know, again, an environment will be an initial input, another species in the environment will be initial input. But there must have been, you know, unless we're talking about a sort of intelligent creator argument, a sort of self-supervised learning that we went through, which trained our evolved features. So self-supervised, so contrastive learning is a form of self-supervised learning that trains models by minimizing the contrastive loss for representations of positive and negative pairs. And it works by sort of the loss functions make the positive images, positive pairs, as close to each other in space as possible, whilst making the negative pairs as dissimilar as possible. And this sort of contrastive learning works by comparing an unlabeled image to positives, which is the same image with certain augmentations, meaning color shift, contrast shift, crops, and negatives, which is all the images in the data set. And this self-comparison means that images are not compared to a labeled category like in generative learning, but almost that each image itself becomes its own category. The data augmentations are changed to the image, are changes to the image in a way that should change the data, but not compromise the important features of the image. For example, having different versions of the image with different color palettes with these dogs allows the algorithm to not learn to sort of cheat the image recognition by solely focusing on the color, but rather to learn the features, which will not be lost by simple sort of data transformations or augmentations. And by comparing each image to versions of itself in the same kind of sort of normalized hypersphere as we talk about, and trying to sort of reduce the distance between the positives, each image can be made to be sort of perceived or seen by the algorithm in a way that ignores non-useful features but focuses on useful ones. Such as seeing arms and legs and snouts on a dog rather than just the color. This system also compares each image to its negatives, which are the other images in the data set, and tries to maximize the distance between any image and its negative, so that the data set doesn't just converge into sort of one spot on the hypersphere. In an ideal situation, the learning features are quality when similar images, such as two different photos of dogs, are placed closer to each other in the hypersphere than two dissimilar images. So a sort of a dog and a, you know, man playing the French horn, whatever that is. And the pairs of these sort of dogs are not matches, but the ideal feature set will sort of place them in similar spaces on this sort of natural image manifold. Yeah. It has been shown that these sort of algorithms can be far more useful than supervised algorithms, first because they ignore bias, and many of the problems associated with labeled data sets, and oftentimes they can end up developing far better features for image analysis than supervised sets can. This has also been shown that self-supervised models, the sort of feature representations are very sort of can be sort of mapped onto how our brain works with fMRI, as we learned earlier in the course. However, the models are also not brain-like, because the most anterior regions of the sort of ventral stream recognize, they have cells which are sort of hypothesized to recognize really, really specific images. You know, we have whatever it is, the Obama cell that will fire when you see Obama's face. These kinds of things are very difficult to create unsupervised in the machine learning algorithms. This might be because even though the self-supervised augmentations are somewhat random, they are still biased in ways that we can't see yet. And so we're trying to find this sort of self-supervised learning that has this sort of unbiased nature. But how can we have these augmentation? How can we sort of learn more about what kind of augmentations will be useful to sort of find unbiased perceptions? And what are the pressures that dictate how networks evolve? So these are sort of loss functions, which are defined by humans, except here in the self-supervised learning. So definitely self-supervised learning is key, but how can we sort of figure out what kind of augmentations we should create? And how can we get to be truly random with augmentation? So an interesting starting point for here is StyleGAN-T. So StyleGAN-T basically develops interpolated images. It uses sort of generative adversarial networks as before, in a way that significantly improves previous GANs and outperforms distilled diffusion models, which were previously the state of the art in fast text-to-image synthesis in terms of quality and speed. So this model can develop interpolated images, which goes from sort of one image, which is painting a fox in the style of Starry Night, and will create a set of images at 10 frames per second to a beautiful landscape of an ocean, mountains in the background, sun is setting. This uses the generative adversarial network as before, but with a redesigned discriminator. So one of our sort of organisms in our environment is redesigned so that it is pre-trained with a feature network that uses a self-supervised dyno objective. What this basically means for our question of sort of unbiased generation is that the discriminator itself can have any input bias eliminated. Rather, this can be kept to the generator. So we can still have this sort of idea of having a desired prompt, but whilst eliminating as much bias as possible. Again, you know, self-supervised dyno is still going to have some sort of human input in what kind of variation we have, but it's still getting better and better. Interesting as well, these strong interpolation abilities are very useful for other things, such as actually exploring the bias itself. So ZSOLNAI-FEHÉR in the 2-minute paper YouTube channel showed us that these iterative generative adversarial networks can be used to iterate through different versions of a possible image in real time. This is incredibly useful for designers for obvious reasons, who want to sort of look through different versions of materials or output images. So for example, here, the channel shows us that you can sort of drag this sort of black and white circle around this sort of heat map, and the heat map is almost a sort of representation, a 2D representation of the sort of natural image manifold that we know that exists on this hypersphere. And you can sort of drag this pointer around to see different versions of what the font might look like. This is again, so this is an algorithm which creates a font, and all of this sort of heat map is a bunch of different types of fonts which might be created, and you can interpolate between these. The reason this is really interesting, again, is not only useful for designers for sort of finding variation, finding exactly what they want, but it's very useful when we try to consider what kind of variation we have generally in our AI, because we can explore the feature manifold in real time, which allows us to intuit what kind of AI generation or sort of image generation we are actually creating. And this hence allows us to realize what selective pressures we are placing on the AIs. Through this, we can consider what kind of variation we have, again, in our imagination itself, our perception, and sort of come closer to finding out what kind of bias we have away from, the truth in our perception. We can also sort of explore this manifold of these sort of so-called correct outputs, and get a closer understanding of what our biases are. Thank you very much for listening, and I'll see you soon.